we derived the climb and descent. Okay. We had the climb condition and we derived the expression, that is V is positive in this, and we got the expression for induced flow as okay, and then nu h is over inflow, and we also wrote V plus nu over nu h. This is the velocity at the rotor disc. Okay. This is and then the far field we wrote this V plus 2 okay. These are the expressions we got for the climb. Similarly, we derived for descent using a different set of condition, in the sense I will write here descent or descent if you want to call it, or descending. Okay. Okay. Here our diagram was slightly different. We used the direction of velocity, we put it up, and here we said V minus nu, and we made it V minus W. Again W is 2 nu, even in this case. Okay. So, you know, and thrust is this way, nu is down, but in this case V is positive up. Whereas here V is positive down. Okay. And we got the expression. Now I am going to combine and then put it as one big expression, which is much easier. We got the inflow and at the rotor disc is the other way around. I am writing it. We wrote it as minus V over 2 nu h minus plus root of and then 2 nu minus V over nu h. This is minus plus it correct, or you can put it as it's okay, right? Expression, kindly check it here. Here by this I should change it to, this is plus, right? This goes out. Yeah, sorry. Check here. Yeah, because I am multiplying by 2, 2 will go up. Okay. You now have one set of expressions for descent, one set of expressions for climb. You can plot both of them in one diagram. That means I am going to specify, if I want to plot x axis, I say v over nu h. This is basically climb, this is essentially descent, which is a negative value, and the y axis nu over nu h. Okay. Now, you can take this expression and directly plot it, but you have to be very careful, because for the descending rotor we took v up positive. Okay. So, that means here I may mark negative, but actually I should use plus only. On the other hand, if I want to call my velocity, if it is helicopter is going up is positive, coming down is negative, then in these expressions I can just change the sign of purely the velocity. If I change the sign, then you will get that when I use descent I have to put minus v, not plus v as is marked here. Okay. So, if I change the sign, I have to erase this, because this diagram is not directly, because I have used this symbol, because this is much easier for understanding in getting that expression, but in some of the books they give the opposite, in the sense the sign is already taken into consideration in writing this expression. So, if you do that, that expression will become, so I erase this, v is negative downwards. So, here you see, so I am going to simply erase this diagram, and then I will write descending rotor, there v positive, here I will say v less than 0, I will put a minus sign here, and this will become plus, 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 that is all. Okay. Just the sign will change, whereas inside the square anyway, because these are all square terms, so it does not matter. So, only change of sign, you follow. Now, what happens is I can directly go ahead. If I want descent, I will simply put v is minus v, substitute here and get that. Actually, if you put minus v, this will become plus, that is what we had earlier. Okay. You follow. So, everything will be fine. Now, we will plot this curve, assuming that these are valid everywhere. Okay. Suppose let us take only this. This is inflow as a function of climb. Now, climb means I should be on the positive side. That means this curve is applicable only for climb situation. As I keep increasing my velocity, okay, what happens this term, because velocity is v, nu h is fixed, that is nu h is hover inflow, okay, that is a constant quantity for a given rotor. As I keep increasing my velocity, this term will keep decreasing, okay, asymptotically it will go to 0, but a very high values. So, we will just plot 1, 2, 3 and nu over nu h. In hover velocity is 0. So, nu over nu h is 1. So, the curve starts from 1. 1.0, here you may have 2, may have 3 etc., and this curve will be like this. Okay. In the but assume that this expression is valid even in the descent case. Okay, then you know V is negative, because I have to put V negative, then this becomes positive number, and positive this will keep on increasing. So, I will just draw by a dashed line okay. This is an extrapolated curve, okay. That is nu is always positive, please understand. When V is, maybe I will mark here 1, and here mark 2, this is minus and maybe 3. But this will reach technically what? V by nu h. Nu by nu h is V by nu h, that is all, both are equal, which means both are equal curve is what? It is a 45 degree. This curve is asymptotically it will go to this line is a 45 degree line. V plus nu is 0 on this line, because V is negative, nu is positive. So, V plus nu is 0. Okay. You got it. So, if I extrapolate this to the descent, the curve is going to be like this. Now, let us go and then plot. Hey, this is not this is only an extrapolation of what is valid here. Let us plot the curve for descent separately. If you plot that, I hope let us take a slightly different, I will take this color. Okay. Now, let us look at the values where it is. Suppose if V is negative, this value, if V is 2 nu h less than 2 nu h, okay, or V by nu h is less than 2, then this is a imaginary number. That means, I cannot have a root V is okay. I cannot have a root below this. I can draw one more line, I will just draw that. This line is V plus 2 nu 0 line. Okay. This is 45 degrees, this is maybe slightly lower. Okay. Now, my root will start only from here, and I have two roots, because plus or minus both are valid, because there minus is not valid, because inflow has to be always positive. Here I can have both plus minus, both will give positive root, because this is always less than this quantity. Okay. So, I will have one line which is coming like this. Maybe I will draw slightly. Okay. And the other route it will go asymptotically to. So, for every value of this you will have two routes. One of the routes will be above, one will be below. Okay. Now, I have plotted this by continuous line, this by discontinuous line, just to indicate. Now, let us go back to this. This is a problem. I should have drawn this figure there. Okay. Anyway, it is okay. This is the V is positive, V plus nu positive, V plus 2 nu positive. Okay. Everything is positive. So, this is normal working state, this quadrant. Now, when you go here in this V is negative, nu is positive, okay. And then you will find that V plus nu is also, because that is why this line is the border line for this region is vortex ring state. In this zone, V is negative, V plus nu is negative, but V plus 2 nu is positive here. Okay. So, this becomes your, what is that, turbulent wake state. And here everything is negative. Okay. In the sense nu, V is negative, V plus nu, V plus 2 nu, all of them are negative. Nu is positive, please understand. Nu, this is always a positive quantity. What we are writing is V these three all are positive. When you go here, V negative, V plus nu, V plus 2 nu, they are positive. When you go here, V comma, these two are negative, but V plus 2 nu positive. When you come here, V comma V plus nu comma V plus 2 nu, all are negative, and this is windmill break state. Okay. Windmill break state. Now, you see my inflow diagram only in vertical flight is expressed in non-dimensional form into 4 regions, but the continuous lines are valid, but in between line here these results are not valid. So, you have to only do some kind of a experimental estimation, because the flow is highly turbulent, mixed, you cannot get the inflow, because there is nothing like inflow at a particular point. There will be a flow, but you will not be able to get it, you will get some mean kind of a value. So, how do we do it? So, a lot of experiments, of course, theory people are trying to do something, but it is a very tough problem, because the flow is highly mixed. In the experiment you can, they try to take a rotor and then try to design, bring it down, find out what is the power it has taken. From there you somehow, assuming that you will be able to estimate the inflow. Please understand, estimate the mean inflow. I will write that later. Then the curves show like this. Maybe I will draw a different color. Okay. I think maybe okay. So, this is some kind of a experimental, okay. These are all theoretical curve, this yellow is the experiment. You do not get inflow somewhere here, but experimentally measured means what inflow? It is only a mean value you can estimate. Okay. Now, how do we really estimate that? Because we, if you remember last class I mentioned V plus nu is 0 means there is no flow through the rotor disc, and the power is just very simplistic, without the drag power. Okay. Just I am taking only induced power. Induced power is, we know that P induced is thrust into V plus nu, and if V plus nu is 0, that means I do not have any power, but I am rotor is generating a thrust of T, but you are descending. Okay. This is called the auto rotation, but technically you do not take this particular velocity, because you have profile drag also, and then the tail may take some power, and the fuselage also may get a little additional drag. So, usually you design at a velocity slightly faster than this point, slightly faster than here, a little faster, you go a little this side. Okay. This is, I will now, this particular curve is the inflow curve. The same curve is represented in a different form, and that form is the one which I showed you in the last class. Okay. Instead of plotting nu over nu h on the y axis, you plot the total flow through the rotor disc rather than only the induced velocity. Okay. If you plot that, this whole diagram will get rotated, and that is what I show. This was this is the diagram. Essentially, we have rotated that original diagram a little. Now, in this diagram, my y axis is V plus nu over nu h. So, I have added that. So, it is like a 45-degree rotation. Now, you see V plus nu 0 is nothing but my x axis, and then is my 45-degree line, because V equal to, and then this is V plus 2 nu is this line. So, I have split the whole what I showed earlier, normal working state, this is the vortex ring state, turbulent wake, and windmill brake state. Okay. Now, how do I, this is called the universal inflow curve. Okay. Now, how do I use it? Because you see very interestingly this black patch, this is estimated, because you can't do from this equation. Please understand one thing. Okay. This equation is this dash dash dash, that is all. Okay. You realize I can make an approximation in this zone. That means the descent velocity I will take in this zone, I will do an approximation to say what is my inflow. That means I am just going to assume some simple linear expression, okay, and then I will be able to arrive at basically V plus nu. I can do that, I will show you what it is done, and that curve you can use it for predicting any auto rotation situation. Okay. Is it clear? Because this is a very important curve. Even now some publications come, how do I get this zone? Because this is one of the flight condition, because auto rotation is a criteria which your vehicle has to meet certain guidelines. That is, when the engine fails, what are the pilot should take a corrective measure, and it should not come like a stone, it will come down. But we will see, it will not come down very slowly, but it will come down some with velocity. Pilot still has a control, he will auto rotate, he will come and then he will land, okay, without much damage. That is the idea, because this is one of the capabilities of the helicopter. Now, now you see this is not that easy. This region, right at the very simplistic level of the introductory course itself, you will know that there is something which you can't calculate. Okay. You have to, that is where the experience, industry, test, measurements. Of course, pilot go through a little bit of auto rotation experience in flight. Okay, not that they will come and land, they do not do that. They will just do a power off and then try to do, because that is a maneuver they must learn. We will do a little bit on that, because auto rotation is very interesting. Pilots are taught much more in this, but we will not spend too much time on the auto rotation. This is only one of the flight condition. Okay. What we will do is, we will try to get a approximate line here, and we will use that to see how we can proceed further. Is it clear? You have any questions? Because this diagram is, even today you have to make that approximation in that black zone. Some tests are done, you can get some data points, but can you predict theoretically? Okay. It is a very simple, you have a rotor, the rotor is descending, use a sophisticated analysis and predict. Okay. Now, that is a very challenging task, it is not that easy. Okay. Now, that is because usually we do not take, see, the tail rotor power, practical problems, you have a power taken by tail rotor also. See, those are not included in my, when I write the power is only the main rotor, that is number one. We neglect swirl effects, okay. There, even though there is a small percentage, we neglect that. Non-uniform, these are all calculated based on what? Uniform inflow. What we said, non-uniform inflow may change the power, right. And then swirl, then there can be transmission losses. You follow what I am saying? All those things can be there, which is about, see, tail rotor takes some power, and then these losses are also there. So, that is why industry has an estimate, they will say total power. Okay. But what we are doing is only the rotor power, but non-uniform wind load, just to rotor alone, even if you consider, I am not considering my transmission loss, I do not consider my tail rotor, tell me what power my rotor alone will have, real power. Then you find non-uniform inflow, and then tip losses, right, and then you can have swirl. So, these are all the additional effects which we do not model in getting this curve. That is why practical curve they just put it a little, okay, that is all. Now, let us, is it clear, because this curve you will have to use. Okay. So, I am telling you, if you have any doubts, anything in understanding, you please ask me. So, this part is over, because the utility of this equation is only to draw the diagram, that is it, there is nothing else. Okay. Now, let us say for that black patch, this zone here, V by nu h is approximately 1.6 to 1.8, the width. Okay. V by nu h in the range (1.6), you can take it minus 2 minus 1.8 for, please note, for 0, because this is the 0 condition. Okay. It is in that range. Usually it is taken as approximately 1.71, somewhere midpoint. Okay. For V plus nu, is an in between these two, I am taking that point. Okay. I am going to see, it is a very steep line. Okay. So, I will draw a straight line approximation and then write how my V plus nu over nu h, if you take this point, I have to say the coordinate of this point, you can write it as minus, right, comma 0, that is the coordinate of this point. Okay. Minus I am already taking, because it is in the negative descent, and then the coordinate of this point. Okay. Please note, this is the point, because where I have my both the roots come, this is the point where I start having a root for the descent. Okay. Below that I do not know. So, the theoretical curve tells me minus 2 minus 1, this point. So, I will simply, okay, I will draw a straight line between these 2 points, and the straight line will be what you will get. I will write that equation, that is plus okay. This is the equation, straight line equation, because you just use y minus y1 divided by y1 minus y2, x minus x1 by x1 minus x2. This is just a equation, the equation of the line from here to here. Okay. And if you use x bar somewhere between these number, because x bar is what? Basically this, if I substitute 1.71, it will be approximately, say, divided by 2 minus 1 by 1 minus, okay, approximately. This is written as 6 plus, okay, that is all. You will find that if you want to really, because this is not exactly 6, this is about 5.88 or something like that, this will be 3.4 some number. So, you take it approximately, this is my line. Now, you know that I have a inflow estimation in the turbulent wake state. Because why I need an estimate turbulent? You can always say I can extend this curve even here also. Okay, you can take it, it's fine. But normally people are not really interested in having this, because this is purely from autorotation point of view. Okay. Now, you see, even when I descend very slowly, see this line, this is not, see this is the line theoretical, it is slightly up, but it is all right. It is not that this is deviating totally off. So, I make a small error even in my other expression, but it is okay, I can take that inflow if I am coming down slowly. Okay. But you can't use this expression completely even here, because this line will go like this, you understand, and that line will come like this. So, you can have some kind of an approximation. That means, I know my inflow even, but this is inflow means mean inflow, because I really do not know what exactly happening everywhere in the zone of vortex ring state and turbulent wake state, just approximation, and this you can use it for evaluating power or anything like that. Now, I will see how you can really use, because the shaft power, I erase this part. See, the power is essentially to rotate the rotor and you are descending with a thrust. So, you can say the shaft power, this consists of three components we had. One is the climb, it is climbing with the velocity v, climb or descend, it does not matter, T v plus T nu plus your profile drag, because that is, at least we did this, that is sigma 8 rho okay. Actually, true auto rotation means this power must be 0, okay, true auto rotation, because you have this. That is why the velocity with which it descends will not be at the point v plus nu is 0, it will be slightly at a increased descent velocity, it will come. It will not come at 1.71 where it meets v by nu h, it will be slightly more, because you need to cancel this term also, you follow. Actually, this equation, this kind of expression is used to estimate, because you take a rotor, you try to descend slowly, you find out what is the power you require, then you can get approximately from there. If you know this quantity, you know this quantity, because thrust is known, you know V, you can make an estimate of inflow, estimate mean inflow, it is a very crude, and that is how those dark patch is obtained. Now, you see, this is all for our basic climb and descent. See, hover is wonderful, climbing is fine, but the moment you start descending, problem starts. But then you need to have an expression to evaluate quantities, and this is all the expression that is used, because industry will, they will have some approximation, that is all, and that will be based on this kind of a curve. This is a universal inflow curve, and actually this was drawn, I would say 19, when is that? I will show 1947, okay, an alternative by Locke. That curve, this is called the universal inflow curve, okay. So, please understand, because the moment the problem becomes complex, see, one is you have to go deep into the physics, start analyzing it very, very systematically. But otherwise, with what you know, you try to have some approximate but physically meaningful expressions. Okay? And the physically meaningful, which is useful, that comes by practical experience, and that is what these type of curves are. You will slowly realize in this course, enormous approximations are made everywhere, okay, because you can't just handle things completely, because this itself is a problem. You can do a PhD on this. Even today, CFD, you okay, I am going to model, because till rotor CFD is still at the primitive stage. It may come up in future. Get the rotor inflow. I want the rotor inflow when the rotor is descending. Okay, very simple case. Get it and theoretically predict this. It will be good. You get your PhD. Okay. Now let us look at some few numbers. Okay, just for the sake of interest, because this is an interesting part. We said V plus nu 0 is good, this is okay, slightly a little negative number. But what is really the descent velocity for autorotation in practical terms, the descent velocity? Okay. And if you really look at it, we said that very crude approximation, this line meets somewhere around 1.71 we used, because in the range of 1.6 to 1.8 we took that 1 minus 1.7. That means V, very crude approximation. Please note that this equation you take it, because this is important. Okay. So, we said V over nu h in the range 1.6 to 1.8, or you take it approximately. Okay. Now, you can know nu h. Nu h is what? T by 2 rho a, right, or in other words you can take it as what, C t by lambda, what is lambda, nu h over omega r is lambda I, which is square root of, right, and if you take C t, most of the rotors you can take it approximately C t as 0.005. Okay. This number is 0.025. So, your lambda I will be 0.05, and omega r tip speed you can take it as 200 meter per second. Therefore, my nu h will be 10 meter per second. If I multiply, okay, v is the descent velocity. Okay, so, it is a negative number. You will find it will be coming with about 17 meter per second. Okay. So, in the range of 15 to 20, 25 meter per second it will come down. It is not that it will come very slowly like a leaf. 15 meter per second is quite substantial, okay, in auto rotation. But what pilot comes, he will not come and then hit 15 meter per second or 20 meter per second the ground. He will come near the ground, and then when he comes near, then he will try to climb up. Okay, that means he will increase his collective, and then he will try to, it is called flare up. So, he will come and then he will try to go up, and then he will slowly land. This is a vertical Please understand this, whatever we wrote, this is auto rotation in vertical descent, but you can auto rotate in forward flight also. Okay. Actually, they try to auto rotate only in forward flight, they do not come down like this, okay, because you know that this is the shaft power. Suppose if the power required for a given flight condition is less, then automatically you will also come down with a less speed. That is why you auto rotate at a forward speed where the power is minimum, power required for flight is minimum. Therefore, you auto rotate in that particular speed, okay, because that part comes a little later. Right now, it is only vertical up and down motion. Okay. Now, just for some interesting part, it is we will take even this itself. This is T into V plus nu plus, I combine all these things as some Cp profile drag, okay, just profile drag, you rho pi r square, okay, and this I can replace by Ct okay. Nu h over omega r into omega r. Please, I am doing lot of non-dimensionalization just to get some interesting form, rho pi r square omega r whole cube, okay, because I multiply by nu h divided by nu h and omega r non-dimensional. Then what will happen is this term, I erase this part, this is V plus nu over nu h, right. You will find that rho pi r square, if I set this shaft power for auto rotation condition, power must be 0. So, this term will go off, this entire term will go off, and this is lambda induced, which is root of Ct by 2. So, I will get here Ct power, okay, plus sorry into okay. That means I can V plus nu over nu h is nothing but minus Cp, this is the profile drag, whatever all the drag, Ct power 3 by 2 under root 2. Now, you know that as a proportionality, this is nothing but CD naught, profile drag is proportional to drag coefficient, thrust is directly lift coefficient, okay. If you want to have a low descent velocity, okay, if this term is less, CD naught over CL power 3 by 2, this also relates to your airfoil characteristic, okay. If that value is small, that means your auto rotative descent velocity is also small, okay. And that is how in the selection of airfoils for because of course, it is not that one airfoil you can choose, because the rotor blade is a long blade every section, but this is one of the interesting part, okay, where, and you will find that if you normally substitute the values of CD naught over all these things, this is approximately around minus 0.3, 0.4, 0.3, something like that. That means V plus nu over nu h is about minus 0.3, 0.4, which is, this is the y axis, V plus nu over, that is around, this is 1.3, maybe somewhere here. So, you are descending at this velocity. Okay. So, you can get from this value. Now, you see, you will be descending with a lower velocity v if this quantity is small. Now, you can plot the curve of an aerofoil, CD naught drag coefficient over lift coefficient power 3 by 2 for various angles of attack, okay. And that will tell you what is the minimum angle of attack you should operate, because if you operate at a minimum angle, that curve I will show, because this is a very interesting part, because efficient angle of attack for auto rotation. Okay. So, you know that this is the one, let me erase this part. Now, you can see this is a efficient angle of attack for auto rotation. Okay. When you say efficient, you want minimum, see, you do not want to come fast, you want to come slowly, okay. Then you can land very safely. So, you want to come slowly means, if I can come slowly, if this quantity is small, that means CD naught over CL. So, I will plot a curve for, this is CD 0 over, as a function of, this is angle of attack. See, this is, you can plot only for aerofoil this, okay, for an aerofoil, because the rotor is not, because every section. Now, you see, if every section has to operate efficiently, how you have to design your rotor. This curve will be like this, I think this is 0.08, I think 0.4, here this is 4, this is in degree, okay. 4, 8, 12, 16 and 20. The curve will come something like this. Okay. It will go like this. So, you have a fairly wide region for, but below stall. If you go too, again you will go. Okay. This is stall. If you go a higher angle of attack, if you come too low also, it is not good. So, there is a wide range of operating condition for a aerofoil. This is from the characteristic of the aerofoil, you have to draw that line. Okay. Now, there is another interesting aspect also is there, which is related to how do I, what is the angle, because the helicopter is flying, engine failed, because pilot would have given a pitch angle, assuming he is hovering, collective pitch, he has given, the blade is operating at a particular pitch angle, please understand pitch angle, not angle of attack, pitch angle. Now, engine failed, he has to auto rotate. What pitch angle he should have? Okay. If he has a larger pitch angle, the drag will be. So, there is a diagram which is a very interesting diagram. That is purely based on forces acting on airfoil in auto rotation. Please understand, but it is again a very simplistic approach, not with all the turbulence and vortex etc. Very simplistic formulation, but that curve is used, okay, for practical operation. But that is a very interesting curve, because auto rotation, if you really see, it is an equilibrating situation. So, I will just show that part, and I also mentioned, okay, this is just for, since you asked drag, okay, what is the drag coefficient of the, because I am just, because rotor is rotating, thrust is acting up, thrust is there, and this rotor is coming down with a steady velocity. Okay, please understand, when it is coming at a steady velocity means what? That means the drag force, the thrust is basically the drag force, and this is the thrust, which is actually this is coming down, that is the force. So, the drag force divided by what do you normally write? Dynamic pressure area into some drag coefficient. Okay. If you write that, the CD, because that I will show you how that expression came about, because normally what in every, you will write drag force is written as what? Dynamic pressure, some area into drag coefficient. Okay. With the lift force, you will put lift coefficient. Now, the rotor is coming down. So, what is the force? Force is thrust, thrust is acting. So, I will put T equals half rho V square A C D. Now, C D is, that is I am calculating the drag coefficient of the rotor. Okay. This is nothing but T over half. Okay. You can write this as T over 2 rho A over 1 over 4 V square, right. This is nothing but nu h. So, you will have what? 2 over, okay. Now, you know that V over nu h, it is around in the range of 1.71, right. 2 divided by 1.71, you take it, put it there, your drag coefficient will be of the order of, see 1.71, 1.22, okay, somewhere around 1.2, 1.3 in that zone, drag coefficient. Okay. Now, I will just read out the drag coefficient for a actually a circular plate that is solid with an area A, its drag coefficient is 1.28, circular plate. Okay. So, a plate, this is a circular plate, its CD is 1.28, but if it is a parachute, okay, that CD is 1.4 approximately, okay, parachute, and for this it is around 1.2 to 1.3. CD for the helicopter is in the range of for helicopter rotor. Okay. So, you see it is power of vertical descent, the helicopter rotor behaves like a parachute, but of the same area, because the area is If you make it a big one, then well, it will generate lot of force. Okay. You understand? So, it is a very efficient in auto rotation. Now, let us take this is another interesting aspect of auto rotation. That is like I told you, he is flying at a pitch angle, engine failed. What should we do? Okay. Because that by drawing a airfoil, we will analyze that part. Okay. I will just draw today, I may not be able to complete it. That is forces acting on a airfoil which is coming down. So, that means essentially I am taking a section, okay, or you can say a blade element, okay, in airfoil in auto rotation. I will first draw the diagram. You have your airfoil, there is a, this is omega r, this angle is theta, that is the pitch angle pilot has given, but it is in auto rotation means this is coming down. Coming down, let us say it has a u perpendicular, I have drawn it up. Now, the resultant velocity is this. So, this angle is phi. Okay. Now, let us draw, you have your, this is the z axis, this is the x axis, lift is normal to the resultant flow, this is lift and the drag is along that. So, this angle is again phi. Okay. Now, what are the forces acting on that? If you take the forces acting on that is Fg is L cosine phi plus d sin phi and Fx is d okay. It is till now the rotor is rotor shaft is given a power. Now, the power is gone, engine is disengaged. Now, what will happen? This will be rotating because at the instant you will have omega r and the rotor is descends, this is the velocity u p and your lift drag, your F z is actually the weight of the helicopter, that is the thrust you can say. I am talking for one section, but basically you have to integrate over the entire blade. Now, what will happen is if Fx is positive, then what will happen? Because there is no power that is given to the blade and you are having a force in the x direction, airfoil is moving like this, but you have a force. So, what it will try to stop, okay. It will start decreasing its velocity. On the other hand, if your Fx whatever that is written. If it is negative, negative means that force is here, it will accelerate my, because there is a force, it will accelerate my airfoil. So, there is a particular angle, that phi, at which this quantity is 0. That means, there is no force acting on the airfoil in the x direction, x is this. When you have no force, whatever the velocity it has, it will continue to have that velocity, and that is the condition for the autorotation. You follow? You have to get that phi. Okay. Now, we will relate to what is the theta, what is that phi, how do we get that, that we will look at the diagram. Now, the interesting part, I am just throwing it, this is for one section of the blade. My rotor blade is rotating with the omega r, which is varying. Every section is different r. Even if I assume my up is same, okay, near the root what will happen? Omega r is, because what is phi? Let us write the phi. What is tan phi? Tan phi is what? Up by, right, near the root, this is small, that means what? Phi is large, means what? What will happen? If you have a large angle of attack, what will happen? It will stall. Okay. So, now let us draw the diagram, because if I draw, because I am drawing the diagram, later we will, this is root, near root, it will stall, that is all, because the angle of attack is large. Okay. Now, when, as you keep increasing your omega r, what happens? Phi is decreasing. Phi decrease, it will come. Phi decrease means what? This is coming like this. From a large value, it coming slowly. That means, it can come to the condition where autorotation is possible. That means, it is like not that every point is under autorotation. So, there will be one more circle which I will draw. Here, rotor is powered by air, basically. That means, the resultant flow rotates the rotor, all right. So, power from air to rotor. Outside, what happens? If you keep on increasing your omega r larger, that means my drag is more, that means it will try to stop. That means what? Drag is there, means I am actually pushing the rotor. So, there is a drag force. Okay. Air is pushing the rotor in the middle region, rotor is actually dragging. So, this is power from, it is a normal operation, power from rotor to air. This is what the actual operation. Now, you see, only at one particular point somewhere in this whole diagram, one section of the airfoil will have that Fx equals 0. Okay. It cannot have all the points. It is very difficult to have that condition established. Now, you see in auto rotation, it is essentially the integrated effect of this integrated effect. That means, outer region actually I am dragging the rotor, that means I am wasting power. Inner region, the air is pulling the rotor. To inside, it is stalling. That is why near root it stalls means, even though it stalls, you know that root cut out, every region is there. So, you say okay, I neglect, it does not create much lift or anything like that. That is the reason. Now, you see why they neglect that. I gave you 0.15 in the homework, root cut out, throw it. This is the region. Now, the integrated value of air is pulling in this region, their rotor is actually getting that. Net value is 0. That is auto rotation. That means, the rotor blade will continue to rotate at the same RPM. Okay. Now, what is the best RPM? Because if you increase your rotor RPM, because your design RPM may be for some particular value. Suppose you say I rotate it faster, centrifugal force will become tremendously high and the blade may tear off. Okay. That means, you do not want the rotor to get lot of power also from the air, but at the same time you do not want the rotor to stop also. But at the same time you need to rotate at a nominal RPM. Now, this itself is a very challenging problem, it is not that easy. Okay. If you say I want to have a rotor, very simplistic, with whatever you have learnt, I say I am going to calculate the full thing. What should be the angle, which is the best? I must operate. Okay. We can do simplistically from this diagram, which I will do it because it is almost time next class, because if I start that, that is a very, very interesting thing. Next class I will do, but this is mainly for, do not think that auto rotation you must know, power, thrust, that T. This is more of physics. The physics is beautiful physics, but it is not that easy, my dear friend. This problem is all. Now, you see a rotor blade which is pulled somewhere in the middle and pulled back somewhere. Now, you see how it will deform. You follow, because in, so you have to design the rotor blade also like that. It is not a rigid blade, it is a flexible blade. It will start getting a deformation. Now, these things go a little complicated. Okay. So, we will not get into that complexity right away, but there is something which pilot is instructed. When the engine failed, what should do? His job is to reduce the collective, because if he has more collective, that is this angle. Okay. He may stop the rotor, we do not want to stop the rotor, and there is again some operational restrictions. There is something called, I will just show, height, velocity. Okay. Helicopter is can hover, beautiful. That means 0 velocity, I should be able to operate at any height. Okay. But they always draw something like this. Do not fly here. This is called dead man curve. Okay. Because if he is somewhere here, if engine fails, he does not have sufficient time to get into auto rotation, whereas if he is above, yes, he can get into auto rotation, and if he is forward speed, thus he can, if it is too low, if it falls, he cannot have the height to auto rotate. Okay. That is why this diagram is drawn. Pilot never goes and then you will, even though the capability is there, please understand, you do not do those kind of operations. These are all from handling practical application point of view. So, we will take this diagram, I will briefly explain next class, and with that vertical is over. So, you know hover, you know vertical flight. Next topic is the forward flight, but forward flight will run for several weeks, and that will be the real aeroelastic problem. Okay.